So thank you very much for coming, and I see there are still people coming in. But still, we're going to get our presentation started now. So our talk today is called Client-Side Protection Against DOM-based XSS Done Right. Obviously, this is kind of making a little bit of fun of ourselves here. So who is us, actually? So my name is Ben. Together with me today is my colleague Sebastian. And we are kind of PhD students at the university in Erlangen and Bochum, respectively, in Germany. And this is today joint work with our colleague Martin from SAP, who, couldn't make it here. So it's just the two of us. Today in this talk, we're going to talk to you a little bit about a practical evaluation of the current generation of client-side cross-site scripting filters. To be more precise, the Chrome XSS Auditor. And in doing so, in our work, we found that the XSS Auditor is not really capable of protecting us against client-side, so really client-side XSS, which I'm going to talk about a little bit in the beginning of the talk. And so we found a number of bypasses, and based on these bypasses, we said, hey, there needs to be a better solution to do this, so this is something that we will present afterwards. And so before we start, this is something that we got from Steve from Black Hat. Hints for speakers, so good speakers capture the audience and so on and so forth in the first 30 seconds with substance, quality, content coming. Sadly, we have to start with some technical background, so I'm going to try and start cute here. Hope this is visible. Actually, it's not, so it's a cat picture. Sorry, it's some problems with the projector here. Okay, so let's start with some technical background. Well, cross-site scripting. So before we can talk about cross-site scripting, we'll talk briefly about the question, if I am attacker.org, and I kind of open an iframe, for example, and frame mail.google.com, why is it not possible for me to interact with this site, right? Because it would be very easy for me to kind of extract all your emails. And the answer is the so-called same origin policy, which basically is a policy that enforces application boundaries based on an origin. And an origin in this case is the combination of the protocol, the domain, and the port. And obviously, attacker.org has a different domain than gmail.com or mail.google.com, so we can actually execute our own code and kind of script into that. This means that the attacker's code runs in a different origin. So since we're at Black Hat, this is Hacking Conference, we want to know how we can actually bypass that, right? So how can we bypass the same origin policy? We have to take a look at what web applications or applications as such typically do. So they process data, right? It wouldn't make sense if you just had a static website that didn't do anything. You have some interaction with the user, so the user provides you with some data, say, for example, the URL is some piece of data or some input that provides to you. And this data may be, for example, stored, if you think of a guest book or something, or it might be echoed back directly to you. Think of a search page, for example, where you see, hey, you searched for XYZ, and this is something that you provided earlier on. And if we look at this piece of, let's call it data, this is actually something that the user may post as data. If this is not properly kind of encoded on the server side or filtered on the server side, this actually ends up being interpreted as HTML code, right? So this is a script tag that allows me to open an alert box. And what's very important to understand in terms of XSS is that I'm not trying to exploit the server side, but rather this code that I can inject here is executed in my victim's browser in the context of the origin or of the vulnerable application. That means I actually run, my own code runs in your identity on mail.google.com. And yeah, basically, this is why it's called cross-site scripting, because as an attacker, I can kind of script into a different site here. So what can an attacker do with cross-site scripting? Well, you can open an alert box, and you will typically see this quite often. And it's like, wow, an alert box. That is super awesome. But actually, this is just a proof of concept. Opening an alert box is basically arbitrary JavaScript execution that you can do. So what can we do with this? Obviously, we can do things like hijack a session, so you can steal a cookie, for example. But so modern web applications kind of are secured against that. But you can control the victim's browser. For example, Twitter, I could now post something on Twitter in your names, like, hey, this is a crappy talk, let's go somewhere else. What we can also do is we can alter the content of that site. There was actually a very famous example of the German Chancellor's website where somebody found an XSS vulnerability and then kind of posted there that the Chancellor had resigned for some weird reasons. And I think even newspapers picked up on that because the text was on Bundesregierung.de, which is the German government's official website. And And also something that people do not necessarily think about, you can use that to steal password managers' passwords. We did a talk at Black Hat Europe. If you want, check that out. It's pretty interesting work, I think. So, to summarize, as an XSS attacker, I can do everything with the web application, but under URID of this logged-in user. And if we think about XSS, there are actually two dimensions in which we can categorize cross-site scripting. So there is server-side cross-site scripting, which means there is server-side code involved that is vulnerable, and there is client-side cross-site scripting, meaning that, well, obviously it's client-side code that is vulnerable here. And then we have reflected and stored XSS. I think most of you will probably know this. In this talk, we're going to focus mostly on client-side XSS, so let's not talk about the server-side here. Let's talk about DOM-based or client-side XSS. This means basically we have flaws in client-side code that allow us to inject our own payload. And to kind of look at this in an abstract way, we have some data that is coming from an attacker controllable source. If we look at this small example up here, this would be the location hash slice1, which means basically everything that is behind the hashtag in the URL. This piece of data flows through the application, and at some point it enters a security-sensitive sync document write. Right? This allows you to write HTML to the DOM. And in order to, let me go back. If I, rather than having kind of my own name, my name would be, again, script alert 1, then this would actually write hello, then the script tag alert1, and would open the alert box. And in order to find this kind of cross-site scripting, there are two ways of approaching this. One is dynamic analysis, using basically taint tracking. Again, this is like a data flow, so this sounds a lot like taint tracking. There's a commercial product called Dominator, which basically does this in Firefox. In previous research, we developed a tool that doesn't have a name. We should actually fix that, which allows us to also automatically generate exploits. So rather than just showing, hey, there is a flow of data, we can actually generate an exploit exactly for that flow and validate whether it's actually a vulnerability or not. I presume there are also ways of doing this statically, but to be honest, I have no idea how static analysis of JavaScript would work, so we're going to skip that. So how can we, now that we know what XSS is, how can we stop XSS attacks? As an application owner or developer, you can go ahead and, do not use user-provided, so basically don't trust the user, right? That's kind of a policy that you should adhere to in any program. So if something comes from the user, make sure that it's either properly encoded or you kind of whitelist some characters that are allowed in, but don't just trust that the user will not provide some malicious data. Well, you can use some secure frameworks, other magic. Recently, people kind of came up with this content security policy, which has issues of its own. You can do sandboxed iframes, but still, I mean, this is all on the developer side. And you can trust us that the developers often do not adhere to these standards, which I will come to in a minute. And so on the other hand, if you're the application's user, you can, turn off JavaScript. Not sure if you can actually use Google Mail without JavaScript. I've never tried. I think there are a lot of sites that won't work at all without JavaScript. This is just it, the way it is on the web right now. What you can do is you can use a client-side cross-site scripting filter. In this case, client-side means it's deployed on the client. It doesn't have anything to do with client-side XSS, just to make that clear. There is NoScript for Firefox. So Firefox doesn't ship its own XSS filter, but NoScript is pretty powerful. It's also kind of, I think for beginners, it's pretty hard to use. So yeah, that's an issue. Internet Explorer ships one, and most prominently, the Chrome browser from Google also ships one, which is called the XSS Auditor. And this is kind of, state of the art in XSS filtering on the client side. And this is, not really discussed, or not really something that, or there's something that the research community can agree on. Okay, before I will soon turn over the mic to Sebastian, let's briefly talk about kind of results from the study we conducted into kind of real-world vulnerabilities in terms of client-side XSS. And I already kind of spoiled that a little bit. So our approach to finding these is kind of three-pronged. So for one, we have a byte-level taint tracking engine implemented into Chromium. That means for each string that is either in the JavaScript engine or the rendering engine, we can precisely for each character say whether it was hard-coded or it was coming, for example, from the URL, from a cookie, from a post message, and so on and so forth. So basically, we can exactly say this part is not controllable by an attacker, and this might be controllable by an attacker. We then kind of built a Chrome crawling extension and infrastructure around it, allowing us to crawl a large number of sites. And then Sebastian came up with an exploit generator that basically takes this taint information plus kind of the knowledge of how HTML and JavaScript works, and then automatically can generate these exploits. And the results were actually like this. So we ran the experiments on the Alexa top 10K, went down 2 pages from the main page, so-called depth 2, found over 1,600 unique vulnerabilities on 958 domains. That means almost 10%. And we know that we don't have any assurances in terms of code coverage because we're just executing the site as is. We're not trying anything like fuzzing or something. When we validated these vulnerabilities, we actually opted to disable the XSS auditor. Why did we disable the XSS auditor? Just because the auditor can kind of catch a vulnerability or an exploit doesn't mean that there's not actually a vulnerability, right? It just means that obviously Chrome did a good job in terms of finding that. And we then reran the experiment, turning on the auditor. And it turns out that some of the exploits were blocked, but others were not blocked. So we were wondering, so why exactly is that? And so we went ahead and kind of conducted an in-depth analysis into also the code base of the XSS auditor, and found a number of bypasses that allow us to kind of bypass the XSS auditor. And then we reran the experiment kind of with this knowledge, specifically generating payloads that would try not to trigger the XSS auditor. But actually this is what Sebastian is going to tell you about now, so how we can actually bypass the XSS auditor. Awesome.
Okay, this mic is working, great. So I'm now going to talk about bypassing the XSS auditor, but before doing that, I will first talk a little bit about how the XSS auditor actually works. So the attacker model that the XSS auditor, oh, I can hear myself. Yeah. As the XSS auditor tries to cover is the reflected cross-site scripting attacker model. So in this model, we have an attacker over here, and the attacker crafts some kind of request that contains his malicious payload. For example, in the URL or within the post parameters. And then the attacker sends the URL to the victim. And, well, victims click on links or visit other web pages. So the request that the attacker crafted is conducted in the user's browser and running in his authentication context. And this leads the vulnerable website to reflect the payload somewhere in the page. So we can see this here. And this is exactly the attacker model that the XSS auditor is trying to defend against. And he tries to do this by finding these constructs back again in the URL. So here you can see the attacker included his payload in the URL, and we have it in the page. And what the XSS... Was this a question? No. Okay. What the XSS auditor tries to do is, while parsing the document, he encounters different HTML constructs that might be potentially malicious. And whenever he finds such a construct, the auditor tries to find whether this construct is also contained somewhere in the request. And if it is in the request, it will block the JavaScript from executing, and thus the attack fails. And, well, the basic assumption of the auditor is that an attacker is always going to use HTML to trigger JavaScript execution. So that the attacker injects a script tag that invokes a JavaScript engine, or whether the attacker injects an event handler, something like onload or onError, that again triggers some malicious JavaScript to be executed. And basically the idea of the auditor is to prevent these malicious HTML constructs from triggering the JavaScript engine. And that explains the placement of the XSS auditor. So the auditor is placed in between the rendering engine and the JavaScript engine over here. And whenever it finds a construct that is possible, that is capable of triggering the JavaScript engine, it tries to filter it and to match the construct against the URL or the request, and if it finds it, it blocks it. So let's now have a look at the constructs that are able to actually trigger JavaScript execution. And the first construct is very obvious, it's just inline scripts. So whenever the attacker inserts a script tag, the browser will invoke the JavaScript engine. The next construct is dangerous HTML attributes. So for example, the attacker could inject an event handler. We can see it here. We have an image and we have an onload event. And when the image is loaded, this malicious JavaScript, which is just an alert box in this case, will be triggered by the browser. And there's also another way to trigger JavaScript with HTML attributes, and this is JavaScript URLs, which we can see here. So, for example, if we have attributes that accept JavaScript URLs, such iframe source, we can use that to, again, trigger the JavaScript engine. And there's a third way, and this involves external content. So the attacker could just inject a script tag and load an external script that he controls, or he could load, for example, a Flash applet or a Silverlight applet or a Java applet, and all of those applets are capable of executing JavaScripts or of generating requests. And for each of these three constructs, the XSS auditor has a separate check. And what I would like to do now is to go through these checks and explain how the XSS auditor is able to catch those different cases and to see whether the content was actually injected or contained within the requests. So here we have an example of an inline script. So as soon as the HTML parser parses document, it will find such an inline script. And what it does first, it checks whether the opening script tag is contained within the requests, so within the URL or within the post parameters. If it finds an opening script tag, it will extract the first 100 characters of the payload up to the first common sign, and will try to find this in the requests, in the URL or the request parameters. And if it finds it, it will remove the script completely, so actually blocking the attack. The second rule applies for attributes, HTML attributes, and what the auditor does here is he first checks whether an attribute contains a JavaScript URL. So it goes through, when parsing the document, it will find attribute nodes, and it will check for each attribute node whether it contains a JavaScript URL, so whether it starts with JavaScript : or whether the attribute is an event handler, so whether it starts with the letters ON and has at least 5 characters. And if it finds, or if it finds that cases, the auditor will extract the complete attribute. So it will extract this string, onload, alert, and so on, and will try to find this in the request. And if it finds it again, it will remove the specific attribute. The third check applies for external content. So the auditor has a list of different tags that are capable of loading external content. And whenever it encounters such a tag, it will first check whether the script or whether the opening tag is contained within the request. So in this case, this is a script, an external one, so it will check for opening angle bracket and script. If it's an object, it will check for opening bracket and object and so on. And if it finds this, it will look out for the URL attribute. So for script, this is source. For objects, this is data. Or for a tags, this is the href attribute. And it will then have a look whether it can find this attribute in the request, and if so, it will block the attack. So to summarize this, we have the rendering engine here, and the rendering engine parses the HTML, finds different nodes. Then when these nodes are capable of executing JavaScript, it will pass it to the XSS auditor. The XSS auditor will try to match these things against the request, against the URL and the post parameters, and if it finds something, it will block the request or the execution of JavaScript, and if it does not find anything, it will pass the script on to the JavaScript engine. So in this process, we have 3 different phases. We have an invocation phase where the rendering engine decides whether to use the XSS auditor or whether to switch it on. Then we have a matching phase where the XSS auditor tries to find malicious code constructs in the request. And in the end, we have a blocking phase. And now let's talk about how to bypass this. So basically, we have 2 different options here. The first option is we avoid the invocation of the XSS auditor. So if the thing is not switched on, it cannot detect anything. Or we can confuse the matching of the auditor. So if it does not find the things that we injected, it will think, well, this is not injected, and then let us execute the JavaScript. So let's first talk about avoiding the auditor invocation. So basically, there are 3 different reasons why the XSS auditor might be switched off. And the first reason is that the main assumption of the XSS auditor is kind of not true for DOM-based XSS, because the main assumption is that all the malicious content passes the HTML parser, and the attacker always injects HTML. But this is not true. For example, we have in JavaScript code evaluation functions such as eval, such as set timeout, set interval, function, and so on. And those functions will never pass, or the content passed to those functions will never pass the HTML parser, so we will never ever go through the XSS auditor in that cases. Furthermore, we also have the DOM bindings in JavaScript. So we have things like script.source and script.text. So whenever we pass a user-controlled string to such a DOM, such an attribute or such a property through the DOM bindings, it will never go through the HTML parser, and so we will never see the XSS auditor in this case. The second reason for the auditor not to be invoked is performance. So we studied the source code of the auditor, and we found several cases where the auditor is just switched off, although it could have been switched on to filter. And one occasion is the inner HTML property. So we found a bug in the Chromium bug tracker, and we found out that they switched off the XSS auditor for inner HTML assignments because of performance reasons, because it took too long to filter all the stuff and to check. So they just switched off the check. And there's also another check for performance reason, and it's when the XSS auditor starts, it checks whether the URL or the request in general contains one of these 4 characters. So the 2 angle brackets, the double quote, and the single quote. If it does not find any of those characters, it will not switch on the XSS auditor, because it then believes that there is no attack happening. So it only triggers in a very few cases for very few URLs. The problem with this is that there are some attacks that do not require these characters. For example, if there is an injection into an unquoted attribute, you do not need to have a quote to break out of the attribute. You just need to have a white space, and you can just add an event handler, and you don't need any angle brackets for doing that. So this is a minor case, and it happens only rarely, but it sometimes happens. This is also the reason for the next things not to invoke the auditor. So sometimes we also have different ways of getting payloads into web pages. So the XSS auditor assumes that all the payloads are contained within the request. But we, for example, have the post message API, we have the window.name property, and we have XHRs that load external content without being actually contained in the initial request. So whenever there's an alternative vector used for XSS, the auditor will not find it, and the payload is not in the URL, so it will not find that 4 characters that are required to switch the auditor on, so it will just switch it off. So that's it on the invocation side. So now we are talking about string matching issues, and now I would like to give a few demos of this. So now we are trying to like confuse the XSS auditor not to find certain strings. So let me switch to the browser. So I will do the demos in 2 browsers. So here we have our browser, that's our patched browser that has the taint tracking engine built into it. And we switched off the XSS auditor in this case. But I will use this to get an understanding of the vulnerability, and then I will show it in the canary version. So in the newest version of Chrome that has the XSS auditor enabled, and will show that the bypass are actually working. So let's have a look at the first demo. So this demo is one instance of a class that we call partial injections. So here you can see a website, and it has some value in the fragment of the URL. And here you can see some output of our taint engine. So what you can see here is that our taint engine detected a call to document write, to DOM function that writes stuff to the DOM. And you can see what the document write actually got as a value. And the red value is marking user input. So this is something coming from the user, and the other parts are hard-coded. So what we see here, we have a very simple script. It just has one variable, and it has this value over there. So and if I change this value and reload the page, we will see the new user input. So the usual way of exploiting this would be doing the following. So we would like break out of this variable, and then we would end the script tag, then would open a new script tag, say alert1, and then close the script tag again. And if we execute it, we should see an alert box. And we do it because the auditor is switched off. So now let's try this and copy this to the canary version of Chrome where the XSS auditor is switched on. We do this and we see the message, well, this thing was blocked. Because what happened is that we injected a new script tag, and as soon as the parser discovers the script tag, it will check if this is contained in the request. It will see that this is actually contained in the request and block it. But if we watch closely, we see that we already have a script tag here. So, well, there's no need to close one script tag, then open another one, and then have our malicious payload. So we can just reuse our existing script tag. So I just remove the closing and the opening tag. And we will again see the alert because the auditor is switched off. Now let's go to the canary version and reload this thing, and we see an alert 1. And in this case, what happened is the matching rule for scripts didn't apply. So the auditor checked whether there's an opening script tag somewhere in the request. But there is no opening script tag, we just removed it. So this triggers the request. So we bypass the auditor. For this class of bugs, we have three different instances of bugs, but I don't have the time to show all of them. So let's see the second class of attacks. So the second class of attacks we call trailing content. And we again see the output of our taint engine. We see we have a div tag written via document write, and we see some user input is passed from the URL, which is the thing. So the usual way again would be to break out of this HTML attribute, then close this div tag, then open a script tag, and so on. But what we see here is interesting. So we have the user input, which is 80, and then we see some trailing content behind the thing, which is in this case a PX. And we actually can use this trailing content to confuse the XSS auditor during its matching. So what I'm doing now is I break out of this div tag, and I just insert an image tag and give it some arbitrary source. And I will use an on-error event. And here the interesting part starts. So I will now type in alert1, the code that doesn't matter, alert1. But instead of closing this image tag, instead of closing this on-error event handler, I will just leave it open. And you will see what's going to happen. So we'll see the alert box, the auditor is switched off. But what we see here is that basically we create a new image tag. And the image tag consumes the trailing content that is behind the injection. So we see that the on-error is not on-error alert1, but it's actually on-error alert1, and then the trailing content px, and then the quote. And this is actually a syntactically correct JavaScript. So this is perfectly fine. And if we remember the matching rules for attributes, the auditor tries to match on-error until the last quote. So it will try to find this string that I just marked within the request, but in the request we only have the beginning of this thing. So it will never find it. And we can try in Canary. So I switch to the Canary version. Click. Oh, this is the old one. I need to no. Oh. So now we see we bypass the XSS auditor again. So because it's not able to find this thing in the request. And for this category, we also have three different types of attacks, or three different instances. And this one is very naive and very, very simple, but it requires the trailing content to be valid JavaScript. This is rarely the case. So in this case, it's easy because there's just px, which is a very short value. But if you have longer values, it's probably not valid JavaScript. But we also have ways for that, but I don't have the time to show this. So now let's go to the third examples, and this category we call multi-injections. So in our study we figured out that each call to document write or in HTML or to any other function has on average 3 injection points. So it's not like there's one user input, but usually you construct the strings of different user inputs and different hard-coded values, and then you evaluate it or write it to the DOM. And what we see here, we see an output of our taint engine again. We see we wrote an image tag, and we have 2 injection points in this case. So in the naive attack would again be break out of one of these attributes and then open the script tag, and this would not work. But we can make use of both of those injection points, and this is actually very interesting. So we can use the first and just break out of this width attribute and close the image tag, and then we open the script tag. And I do the payload. We can look at this now. So this is only half of the payload, it's not working. So we see we have here a part of a script, and we again have an injection afterwards. So instead of closing the script directly, we close it only after the other script. So I do this and do the closing tag in the other thing. So now we see we have a script tag here, but we still have some content that is hard-coded within the page, and that destroys our attack because it's not syntactically correct. But we can just make use of this and just try to get rid of it. So I just use the void function, which does nothing, and then just wrap this thing in a void, and we see an alert box here. And what happened just now, we have a script tag, and this script tag is valid JavaScript. It has an alert, and then it has the void function, which consumes these hard-coded values so that they don't annoy the JavaScript engine, and then it's a valid syntactically correct JavaScript. But what we also see here is that this is hard-coded actually. So not the complete script is contained in the request, but just parts of it. So let's try to execute this in the Canary version of Chrome. And we see again we have bypassed the filter. For this category, we also have 3 different instances of multi-injections. So we can have this simple multi-injection. We can have a multi-injection where only one value is reflected twice. And we can also have multi-injections where we have different injection points, for example, multiple document writes, multiple inner HTMLs, or we could even mix some of those. But I'm not able to show all of them. So what we did then is we had about 17 different Chrome bypasses after 2 months of studying the Chrome source code, and we also had this huge number of DOM-based cross-site scripting vulnerabilities that we found. And what we did is we patched our exploit generator to make use of the bypasses. So instead of just generating naive cross-site scripting exploits, we checked the vulnerabilities first and checked whether they are susceptible to certain bypasses, and then we generated a specific bypass for it. So we did that, and we were able to bypass the auditor in about 80% of all the cases. So we were able to bypass in 72% of all vulnerabilities and 80% of all domains. So because some domains have multiple vulnerabilities, and we were only able to bypass one, but that's basically enough to exploit a web page. Okay, that's it from my side. And yeah, there's a disclaimer, some of these issues have been fixed, but not all of them, because some are inherent in the design of the XSS auditor. So that's the reason why we thought, well, we need something new, and we implemented our own filter. And this will be covered by Ben.
Okay, thanks. Let me have a quick sip. Okay, so Sebastian just showed you that we have, the auditor actually has a couple of problems. And let's try to abstract what these problems are. So problem number one is the auditor does some approximation of a data flow, right? It tries to guess that, well, something was sent to the server and it was coming back, so there might have been a data flow on the server which occurred, and then so it basically does string matching to approximate this data flow. Secondly, it's located inside the HTML parser, and as we've seen, this is also a problem because we don't necessarily need to inject HTML to be able to execute JavaScript. And thirdly, and to be honest, also towards the guys who designed this, it was never designed to tackle kind of client-side XSS. It was always meant as a defense against reflected XSS. But let's try and fix that. So we propose the following solution. The approximation using string matching is unnecessarily imprecise for flows that occur purely on the client side, right? We have taint tracking in place. So let's use the taint tracking, pass the taint through all the execution path of the application, all the way down to the JavaScript parser. where we can then say, okay, so we have this string that is tainted, and now we can apply some policy where we say that, and again, abstracting XSS means that data is being interpreted as code. And if you think about what a JavaScript engine does, or what any kind of basically any language parser does, it kind of generates tokens out of the text content that is passed to it. And then these tokens might, for example, be literals, they might be declarations, they might be call expressions, and so on and so forth. And we say, this is user-provided data, so it should always end up being interpreted as data and never as anything else. So that's the basic idea. Let me kind of give you a small example here. So we have an easy vulnerability here. We have some user input that goes into this eval, and Sebastian just showed you how we can actually, or similarly, this is similar to these in-script injections we had earlier. And let's presume our input was user data, right? So this is what ends up being sent to the eval function, and this is what the actual kind of abstract syntax tree looks like. So we have a declaration, we have an identifier, and then we have the red part denotes here tainted data, so user-provided data. We are creating a string literal from user-provided data. Again, data is, well, a string literal is obviously data, so this is okay. We're fine with that. However, if we kind of look at the same example in a case where we actively exploit the whole vulnerability, so we break out of this definition of A, we do alert 1 and do the comment signs here, then this is what actually ends up being passed to the JavaScript engine. So we have where A is equals user data, then alert 1, and then, well, this is actually not visible. It's gray, trust me, it's less the brightness of the projector's the problem here. So this is what the abstract syntax tree looks like then. We again see, okay, we have some string literal here. We're still fine with that. We have a literal value down here as well, which is a 1. But in the middle here, we have an identifier, which is tainted. We do not allow tainted identifiers. So this is actually being blocked, and we won't let the execution happen here. And so the policies, this policy I already discussed. So we have tainted values may only generate kind of a string, number, a numeric, or a Boolean literal. There are actually also object literals, but we don't want those to be generated from user-provided input. And secondly, Sebastian told you about this. You can have external content, like using script source, for example, which is then downloaded and executed. And obviously, if you are able to inject some, well, this HTML markup where you do script source equals, then you would the browser would request this external resource, and none of the content would be tainted because we wouldn't know what was actually provided by the user. So in these cases, we say we will not allow any external content to be included if any part of the origin is tainted. That means either the protocol, the domain, or the port. And this is both enforced in the HTML parser, where also the XSS auditor is located, as well as the DOM bindings. There is one single exception to that rule. If it is the same origin of the including page. Because if an attacker was able to upload arbitrary content to the server, well, then we don't need XSS auditors or anything in place, right? You can just do anything on that site. Okay, so with this in mind, we kind of conducted an evaluation of our approach. And first and foremost, we were interested in false negatives. So we ran our approach against the set of known vulnerabilities, and, well, to no big surprise, we caught all of the exploits. This is quite obvious because, for one, we detected them with a similar kind of means, and also these were kind of the test cases for our implementation, to be completely honest. And this is basically the issue. We don't have a ground truth, so there is, to my knowledge, no kind of large set of real-world vulnerabilities other than the one we are having. And so this is obviously a problem. But I believe that if there are any bypasses, these are only related to implementational issues where we kind of lose the taint at some point or something. But I think the concept as such should be sound. More interestingly, we looked at false positives. So in order to get a number of false positives, we conducted a compatibility crawl called the Alexa Top 10K, I think also going down 2 levels, and crawled, well, roughly 1 million URLs. And since each URL contains more than one frame, so think about, I don't know, advertisement typically has their own frame, Facebook likes and stuff like that has their own frames. So in total, we crawled, well, 9.3 million frames. And on 0.016% of those frames, we actually caused an issue, which we presume is a false positive because we weren't trying to attack anything, right? Looking at the domains, this number looks a little bit worse. So on 1.83%, this looks like this might be too high. Actually, we looked at all these cases and found that this was always was just one single component in that site that broke. So it's not like you can't use the site anymore, but rather the advertisement is broken or some very specific functionality is broken. More interestingly, we then, looking at these 183 components, we decided, hey, let's have a look at how many of these are actually vulnerabilities, because if there are vulnerabilities, they are not really false positives if we block them, right? Turns out that half of them are actually exploitable vulnerabilities where the site owners kind of did, well, cross-site scripting by design. So they had, I don't know, eval.html and then had the code in the URL. This might be nice for convenience, but obviously has some security implications. And then the third kind of, well, dimension in which we went ahead and evaluated our approach was performance. And we ran the 4 benchmarks, Kraken, Dromio, Sunspider, and Octane. And so this line here is basically the unpatched version of Chrome. Then we have, these 2 are our patched version of Chrome. The green one is Firefox, and the blue one is Internet Explorer. Very interesting to note in this, you see that Internet Explorer is way faster than any other engine on the Sunspider benchmark. And we did a little bit of digging, and it turns out that, according to Microsoft, the Internet Explorer has a dead code detection mechanism. And so the Sunspider benchmark actually has one loop, which is very kind of computationally expensive. But the value that is being computed is never used outside this loop. And therefore, Internet Explorer doesn't even execute the loop. There are some people who say they have a specific, that they don't have dead code detection or elimination, but rather Sunspider loop detection, and then just, well, don't execute that, but never mind this. What you will notice is that we have 2 different versions for our patched Chrome here. One is called patched Chrome, and the other one is called patched Chrome worst. This is due to the fact that if you think of a benchmarking suite, they will typically use strings, they will use integers, and so on and so forth, but they won't use tainted strings, right? They won't write something to the URL, then retrieve it again and do something with this. So typically, the strings that are being used inside these benchmarks won't be tainted. So we don't have to copy around the taint information all the time. We don't have to check whether a string is tainted, and so on and so forth. So this is basically this left part here is if we just have our normal implementation that checks, hey, is a string tainted? And it's only tainted if it's coming from user input. To get an approximation of what the absolute worst case performance overhead would be, we just kind of flip the switch in the implementation, and for each string, just always return, yes, it's tainted. So we'd always have to copy around the taint information and so on and so forth. So this is actually gives us an upper bound to the performance impact. And you see, so it's about 30% in Kraken, and it's typically less than 20%. I think on average it's about 17%, kind of the worst case overhead, and the best case overhead, or the average case overhead, is roughly 7%. This can be optimized, but I mean we are researchers. We're not software engineers at Google. Well, Sebastian is kind of now, but that's a different story. But it was never intended as kind of a mainline patch to begin with. It was merely a proof of concept that it would actually work, and I believe it does. Okay, concluding. What do you want to take away from this talk today? So we showed to you today in this talk that client-side cross-site scripting is actually a big issue. Roughly 10% of the Alexa top 10K carry at least one cross-site scripting vulnerability. This is due to the fact, or I think this number will be higher. Right now, we're not trying to log into any applications. We're not trying to kind of cover much code that would execute kind of additional vulnerability or additional vulnerable code. So this is pretty much a lower bound. I actually conducted an experiment, I think 2 weeks ago, and we're still cross-site scripting 916 domains on the Alexa top 10K, and this is going down 1 level from the start page. And just spoiler, at least 2 of the companies that sponsor this event are also within that set. Never mind. Right, so we then went ahead and conducted a security analysis of the XSS auditor. We found several bypasses that allow us to, well, either bypass the invocation or that, trick the string matching algorithms such that the engine doesn't think that there's actually a data flow happening. And based on this, we propose a new approach to client-side XSS filtering, which uses precise taint tracking and has pretty low false positives. It does have some overhead, which we believe can be optimized again if the V8 developers pick up the idea. Okay, and with that, we're actually finishing a little bit early. We would like to thank you very much for your attention and are happy to answer any questions you might have. Do we have a mic or something, or you're just supposed to scream? You're just supposed to scream, I guess.
Yeah, so let me check. For the XSS auditor, maybe you could bypass the filters. But what I have experienced while doing the static analysis, the commercial tool which is available in market, right now they have they analyze the data flow analysis from source to sink. So what I have observed in my experience is maybe you could bypass the XSS auditor, but the way the static analysis, I have seen your comment that you don't know whether static analysis is working or not. But I am telling you just that static analysis is giving you 100% good result if there is any DOM-based XSS. And the OASP is ASAPI filter, if you're using it, I think you could not bypass what you have done in this dynamic analysis or the manual analysis.
Okay. Well, yes. So I mean, yes. Obviously, you're perfectly right. We have no idea of how static analysis does work for these cases. To be completely honest, I believe that tools, be they static or be they dynamic, would definitely help developers in kind of fixing their software, and then obviously, well, allowing us, if any, obviously not to exploit the vulnerability to begin with. In our work, we found that oftentimes developers will kind of, so they seem to lack kind of knowledge of the APIs that are used in JavaScript, for example. So we found a couple of things where you look at the code and you see like, no, that's not a vulnerability. You look at the code again and again, and then after some time you figure it out. So oftentimes it's really tricky to get exactly what the vulnerability is. But well, to be honest, I think 85 to 90% are really face palms in terms of, it's like really, these examples we had on here is like document write, user input. This is something you see all over the web. So I think, yeah, but also, I mean, the XSS auditor is meant as a kind of a last line of defense against cross-site scripting, right? If we were in a perfect world, there would not be any cross-site scripting to begin with.
Honestly, I mean, I saw a few of your test cases. I think I will use in future also if I will be doing the manual pen test.
Okay.
For the DOM-based. But yeah, another thing, that's what I'm saying. For the dynamic analysis or for the pen test, I think your script, what you have done the research, it is useful for us, specifically for the security community.
Okay.
And, but for your knowledge, I'm just telling you, DOM-based XSS could be found by this static analysis.
Okay.
Very well.
So maybe a remark from my side. So I don't really believe in static analysis tools right now. So I had a look at a lot of them, and they all fail. They wouldn't detect this. And I think the reason is not because static analysis in general is not good, but I think the tools are not good. Mostly because tools are transferred from other languages. So you have that C and Java static analysis tool, and then you say, oh, we want to have JavaScript capabilities. So we add another parser, and then we find all the vulnerabilities. But I think most of the tools lack a lot of really fundamental or basic knowledge. For example, most of the tools don't assume JavaScript to be run in a web page. You just pass JavaScript to the static analyzer, but there's more to a web page. There's HTML and there's CSS and there's other stuff happening. There are events that are automatically invoked by the browser, and static analysis tools right now do not cover all of that. So,
and also we are currently working with people from UCSB. They are trying to kind of build a static analysis tool, and we gave them some of our samples. So it's still ongoing research, but it would be very interesting to see kind of, given the, I mean, we know that there is a vulnerability. We don't necessarily, well, we can actually also trace back where it originated from, but it would be very interesting to kind of have a tool that looks at that statically and say, hey, this is actually a vulnerability. So this is something that is ongoing. Just talked to those guys, I think a couple of months ago. So this is something that is definitely worth investigating.
Yep, thanks.
Cool.
All right. Okay. First of all, great talks. So I'm wondering, what are the functions to define as the source of the taint?
So we basically use anything that the DOM-XSS wiki notes as a source. This is, for example, everything that is the URL, that is referrer, that is cookies, post message, window name, local storage. Am I missing something? So I think basically that almost everything that is not necessarily like easily controllable by the user. For example, a cookie isn't something that you can, as an attacker, easily craft, right? But we still consider these to be sources.
So it looks like there's going to be, I guess, false positives in those cases, where you retrieve some data from cookie or from web storage or those places, because those can be just regular data, right? Regular innocent data without actually user able to control their content.
Yeah, so I think that, well, in many cases, we actually found, well, by kind of manually looking at that, some vulnerabilities where we actually had kind of a flow to a cookie, and then on the next page reload, it would actually eval the cookie for, I don't know what reasons. And
right.
this would...
I totally agree. Is it possible for those fields to contain taint? But it's also possible that for those fields not contain taint at all, right? Like those fields are not controlled by attacker at all.
So it depends, yes. So we have those cases where we have flows into, for example, local storage and out of local storage again, and have cross-site scripting because of that. But I think it also depends on the attacker model you're looking at. So, for example, recently I found XSS on Wikipedia, which was so what they did is they cached a jQuery version in their local storage. So they thought, well, why load jQuery at each page load? We could just store in local storage. So this is not really exploitable at first sight, but think of, for example, you're in a wireless LAN at the train station, and you have an active network attacker, and you know it because you're in a train station. You wouldn't log into your Wikipedia account, but what the attacker could do, he could just inject a frame and change that jQuery entry and put like a little bit like a cache poisoning attack. So he could change that thing as an active network attacker. Then you go home with your laptop and you're in the secure network again and think, yeah, now I can use my password and my email address to log in. But then there is that code already that Wikipedia just evolved in the context of their application. So this is something where you could argue there's an uncontrollable local storage value, but it's still kind of exploitable depending on the attacker model. Okay,
so what about the sanitization functions? So do you consider client-side sanitizations?
Well, I mean, so in the end, if you use, for example, encode UI component or something, and you pass something so you have a string, and you do encode UI component on it, and then you do it, or you use escape, it's a better example, and then you pass it to eval, right? So as like the example showed, like var a equals and something, then actually it's still tainted. But you can't, because you're now using a sanitization function, you can't break out of the string definition, so you can't execute any JavaScript. So it's not like there is no way that any built-in functionality would automatically clear the taint. There is, in our implementation, a means where you can actively, as a developer, you can say, I want to lose the taint information now. But then if you do that, then it's your own fault, right?
Right. So
to answer the question shortly, so we didn't regard in these experiments we didn't regard client-side sanitation. We just said if we detect a sanitizer, we say it's safe. We assumed that when somebody uses a sanitizer, it's correct, but that's in reality that's not really the case. So I think that's an open point where we could improve the detection capabilities to also.
Right. I totally agree, and I think the problem is how would you define a sanitizer? There could be just a user-defined function to loop through the string and look for some character, something like that. I think that would be the really hard part.
Yeah, it's very difficult, and I think we have a new version of this engine, and I think in the new version we are kind of able to do it, but it's very difficult because what you, for example, see is people use regex for URL parsing, and they also use regex for sanitizers. So if you can bypass a certain regex, is it now that you bypass the sanitizer, or that you just bypass the URL parsing function that extracts a parameter from the URL? So this is difficult, but we have kind of ideas to do that.
Cool. All right. One more question. So is your taint tracking on the byte level, on a string level, or on the object level, basically?
So basically the implementation works such that we can, so for each string that is in memory, we kind of allocate the exact same amount of bytes behind the string. And we have kind of so for basically for the first character, in order to get the taint information, you would go to first character plus length of string, retrieve that byte, and in that byte we actually have kind of encoded the source. So for example, is it the location, is it the hash, or is it something else, as well as the 3 built-in encoding functionalities. So there is actually a bit that is being flipped on and off. For example, if you call escape, then we can actually still see the flow of data, and then in the end see, okay, this went through escape at some point, so it's encoded. So this is for each byte, or for each character in the string, there's 1 byte allocated, which holds this taint information.
So do you also record the whole data flow, or only the source and the sink?
Pardon?
Do you record the whole data flow of how the tainted string
So our new engine does that, actually. The old one doesn't. But in the new engine, we're just in submission of a paper that kind of focuses on just that, to also find out how often is a string touched between source and sink. And I think the maximum case is 290 times. So 290 operations on the string. So this would also be very interesting to see whether static analysis would actually do a good job in these cases, or it would not. So, but this is something that is basically upcoming in the new version of the tool.
Okay, very cool. Thanks.
There's another question to your left. I hope your talk is tomorrow. If you have a sore throat.
In the morning. Cross-site scripting attacks is something that web application firewalls, which protect many web applications, protect against. Is one of the vectors that you managed to bypass the XSS auditor was done on application that was protected with web application firewall?
I mean, I guess so. So we crawled a lot of websites, but we did that in a completely automated fashion. So we didn't check all the cases manually. So yeah, we have a lot of vulnerabilities that actually not triggered. So we generated roughly about 180,000 exploits, and we triggered on 90,000 of the exploits. But it's also an open research. What happened to the other 90,000? Why they did not trigger? So maybe this is one of the cases where...
Yeah, but also one important fact to note is that oftentimes the payload is stored in the hash of the URL, and the hash isn't actually sent to the server. So the web application firewall, even on the server side in the log files, you won't see anything because it's in the hash, which is not being sent to the server. And even then, so I'm not sure. Well, I recently found a cross-site scripting vulnerability, DOM-XSS vulnerability that was in a search, so in a get parameter, which was definitely being sent to the server in a, well, how do I call it, like a large online vendor. I don't want to be too specific here. And I'm pretty sure that they have something like that in place, right? So they will have some form of web application firewall that tries to detect these payloads. And in this case, it went through. I can't really say, I don't know. I could ask them, say, hey, do you have a web application firewall? But the most famous example of a web application firewall fail that I found was, there was a vulnerability we were trying to exploit, and it didn't work in an automated fashion because the web application firewall would actually block us. But then I looked at the URL, and there was a second parameter which looked a lot like base 64. And it turns out that they would actually have this parameter that was also really in the get parameter. And inside the client-side JavaScript code, they would decode the base 64 and then eval it. And obviously, the web application firewall has no way of determining that this is actually base 64. It has to decode it, and so on and so forth. So again, I think a web application firewall does not really help in these edge cases, at least. But yeah, I mean, we don't know. It would be interesting to see whether we would actually get errors from a web application firewall if we triggered, or if we try to trigger something. That's a good question. That's something that we can definitely think about. Yeah, thanks.
Thank you.
Okay, are there any more questions?
So I have seen you have evaluated on Internet Explorer. So are you doing it as a plugin?
So we didn't. So you mean these statistics right here, right?
The XSS you have implemented for the taint tracking stuff.
Sorry, now I'm blind. Sorry. Okay, so We didn't. So can you restate the question? So just to get it right.
For the cross-site scripting detection in the Internet Explorer, are you detecting it by implementing it as a plugin for Internet Explorer? Or?
So for this work, we didn't try to do anything with IE. What we did do, so for previous work, we kind of had vulnerabilities that would only trigger in Internet Explorer because Internet Explorer doesn't encode, for example, the get parameters are not encoded automatically in IE. And what we basically did is we had one crawler site that would just open a pop-up, and the payload would then be to send a post message from this pop-up if the payload triggered back to our main window to validate it. But we didn't do any kind of plugin development for IE or something. But the XSS filter in IE is kind of shipped from Microsoft directly.
I see.
Okay. Well, it's 4:30. Then let's go back to the cat picture. No? All right. Well, then, thank you very much. Hope you enjoyed the talk. Thanks.